Section 5.5 is complex eigenvalues, and this will essentially complete our coverage of the eigenvalue eigenvector problem in chapter 5. So we've seen eigenvalues from real valued matrices A that were all real at this point, right? So in other words, we got a real number every time we tried to calculate an eigenvalue for an n by n matrix A. Well, we can actually generate a complex eigenvalue from a matrix A of real entries. So even if A is all real numbers, we may find that it has a complex eigenvalue. And a complex eigenvalue is a complex scalar for which there exists a non-zero vector in Cn. So in other words, this is an n-dimensional vector with complex numbers as entries. So if we're talking about 2 by 2 matrices, then it would be C2. So it would be a 2 vector with each entry in that vector being a complex number. Remember, a complex number is a number of the form A plus BI. So Z being a complex number is A plus BI, which means that, and well, I is the imaginary I, the value for which I squared is equal to -1, if you remember that from algebra or complex variables or wherever else we might have seen it. Now, B might be 0, in which case that means that this Z is a real number, right? There's no imaginary part. Or A might be 0, which means that Z is purely imaginary or a strictly imaginary number. Or it could be somewhere in between. One or the other could be 0. They could both be 0. And we're dealing with the set of complex numbers. So the point to all of that is to say that real numbers are complex numbers. They're a subset of the complex numbers. So we could say real numbers are a subset of the complex numbers. And the imaginary numbers as a set, these are all the numbers that are some multiple times I. They're also a subset of the complex numbers. So just remember that when we talk about complex numbers, we're talking about generally this larger set that subsumes both the real numbers and the imaginary numbers. So anyway, and a vector V in Cn is one for which all of its n entries are from the set of complex numbers. And then lastly, of course, if we're talking about a complex eigenvalue and its eigenvector, well then sure, lambda is some complex scalar, but A times the vector V is equal to lambda V. Remember, that's our definition of an eigenvalue eigenvector pair for lambda and V respectively. So we're given a matrix A equals 0, -1, 1, 0. And let's observe some things about this matrix. This is actually a linear transformation from X into A of X in R2 that rotates a vector X by 90 degrees counterclockwise. Okay, if we go back to our old matrix of rotations, if you remember this, A is equal to, and if we're going to rotate by 90 degrees counterclockwise, that's positive radian. So it's actually cosine 90 degrees, negative sine 90 degrees, sine 90 degrees, and cosine 90 degrees. Remember, this is our standard rotation transformation for 2 vectors, for R vectors in R2, that is. And it's cosine phi, negative sine phi, sine phi, cosine phi, reading along the rows. And in this case, phi is 90 degrees, the angle by which we're rotating. And what we get from that is 0 for cosine of 90 degrees, -1 for sine of 90, and similarly 1 and 0 on the bottom row. This is the exact matrix we're looking at. So we know that this is, yes, confirming that it's the matrix we get from putting in an angle of 90 degrees into our standard matrix of rotations, transformation rotations. Then, yeah, we arrive at the given matrix. So some interesting facts about this matrix is that if we rotate a vector 4 times, we rotate a vector by 90 degrees 4 times, we'll have rotated 360 degrees. So the vector that we end up with is the same as the one we started. Okay, so we can show that down below. Also, though, there's no non-zero vector in R2 in other words, vectors of real numbers, two vectors of real numbers, such that ax is equal to x. And we could even extend this argument for this, ax equals lambda x. And well, we don't really need the lambda x because we know that our rotations are not rescaling, right? We know that it maintains the length of a vector, but it doesn't, it just simply changes its orientation, it rotates it by 90 degrees without rescaling the vector. That was one of the things we proved about this, this rotation transformation matrix. Okay, so really there couldn't be this situation, but we can even argue that that doesn't exist either, even if we did have a matrix that might rescale. And we'll see down below why that might be. So notice a couple facts. First, a squared. If we do a times itself, we have this product right here. The result of that is the negative identity matrix, incidentally, right? We carry out that matrix multiplication. If I want to find a to the fourth, well, then I'll just do a squared times a squared. Right? This is just a little shortcut in our calculation. So I pick up this matrix and square it, it times itself. And so I have this product over here. This is all going to be a to the fourth. And notice what we get out of this is the identity matrix, 1, 0, 0, 1. Okay, so we're confirming that a to the fourth is the identity matrix. So a to the fourth times x is equal to I times x, and the identity matrix times a vector is just the vector. So yeah, we've demonstrated and proven that a to the fourth power x is equal to x. So yes, of course, if we rotate something by 90 degrees 4 times, we end up where we started. Now, similarly, if ax was equal to x for some vector x in R2, okay, so we just write that down and say, okay, say this is the case. Let's carry out what this means, right? Let's write down the consequences of that. Well, then a times x is this explicitly, times this vector x has components x1, x2. And if that's going to be equal to x1, x2, in other words, the vector x, well, then that's going to imply some things. It's going to tell me that negative, so this row times this vector is negative x2 equals x1. So I get this equation. Also, it tells me that x1 is equal to x2. Well, that's that equation. Well, if we look at these equations, there's a bit of a symmetry or almost an anti-symmetry in some sense. x1 is positive x2 and x1 is also negative x2. Well, x2 is free, I guess, in this system of equations, so we can choose it to be whatever we like. And if we do, well, we realize that we get a contradiction for anything but 0. I guess the better way to go about doing this would be to take this system of equations, flip them around. So, write this as x1 equals negative x2. And when we add these, we get 2x1 equals 0. And that tells me that x1 has to be 0. If x1 has to be 0, so does x2 by this equation. So maybe that's a better way to say it. In fact, maybe we don't have a free variable for x2. In fact, we don't. This system forces us to have both components being equal to 0. So that my first line of argument was not good, but this is fine. We could see if we solve this system thoroughly by elimination, that we'll have that both the entries are equal to 0. So what that says is that if this is the case, right? If we write this down, the only way this can be true is that the vector x is 0. Well, that's a trivial solution to this problem. And it's also the 0 vector. The 0 vector cannot be an eigenvector. So it turns out there's no real valued vector. There's no vector in R2 that's an eigenvector for this matrix A. Seems like a funny thing. Most of the time we were able to find at least one eigenvector for any given matrix. So this is going to be what this section is really all about. Kind of the telling thing about this is the fact that we're looking for a vector x in R2, not C2. So it might be possible that there's actually an eigenvector that's in the complex space C2. So in other words, two vectors with complex numbers as their entries, or two tuples with complex numbers as their entries. The other thing we could say is this: I mentioned lambda, right? If we're going to do this truly as an ax equals lambda x scenario, this is what that looks like. If you put a lambda in here and you solve for each of these, you'll find that the only way this could be true is if lambda was equal to 1, right? If we solve for x1 in this equation, what we'll end up with is x1 equals -1 over lambda x2, and x1 is lambda x2. Well, that's only possible if lambda is equal to 1. It can't be that lambda is 0 because we're dividing by lambda, so that's undefined. And beyond that, we'd still end up at the same place we do. We've already considered the case for lambda is equal to 1, and again, that meant that x had to be 0. So there isn't any eigenvector or eigenvalue in the real numbers. In other words, lambda up here that fits into this equation, right? Not any real numbers, at least. So lastly, let's look at what the eigenvalues of A would actually be, right? So if we were going to try to find the eigenvalues of A, and we'll connect this to everything we've done above so far, then we do 0 is equal to the determinant of A minus lambda I, with lambda an unknown. So that's the determinant of this matrix, 0 minus lambda along the diagonal to get negative lambdas. And then the determinant of that is lambda squared plus 1. Well, 0 equals lambda squared plus 1. This is that equation. And if we start to solve for it, we realize, well, if we look at lambda squared plus 1, first and foremost, we know that that's an irreducible quadratic. In other words, it doesn't factor over the real numbers. If we put it into the quadratic formula, we're going to find that it has complex roots. There'll be a negative under the discriminant. But when we solve for it here, because it is straightforward to solve for, we subtract 1 from both sides. Lambda squared equals -1. And as I reminded us up above, we take the square root plus or minus the square root of -1. Well, the square root of -1 is the imaginary I. And there we have it. Remember that I squared, again, is the number that has the property, or I is the number that has the property that I squared is equal to -1. So there we have it. So this matrix actually has imaginary eigenvalues. Now go back and look at A. The matrix A is on its own, it's a real valued matrix. There's no imaginary or complex numbers in there yet. When we go to solve for its eigenvalues, we find that its eigenvalues are plus or minus I. Okay, so, and another theme in all of this that we'll see, we know that this is a rotational matrix. We're going to see that complex numbers, complex eigenvalues for matrices indicate that there's some kind of rotation or periodicity to the matrix, right? To the transformation that the matrix represents. In this case, explicitly, we saw that by periodicity, we mean that eventually we end up back where we started. And we saw that for this matrix, a to the 4th x was equal to x. So if we apply the transformation 4 times, we end up back at the original vector. And then if we were to do that again, we would just keep cycling through in this periodic behavior. So periodicity, on the other way to think about it, is rotational motion if we're thinking about dynamics. But this is a key concept and a valuable tool when considering eigenvalues and eigenvectors in their applications later on. So we're given a matrix A here, 50, -60, 75, 110 by rows. It's a 2 by 2 matrix. We're asked to find the eigenvalues in the eigenspace of each eigenvalue. So the usual, 0 is equal to the determinant of A minus lambda I. So we've subtracted by lambda along the main diagonal. We take the 2 by 2 determinant. It's pretty easy to do. We get this characteristic polynomial out. Our characteristic equation is this polynomial equals 0. It's a bit complicated, so we might as well just jump straight into trying to find its roots by the quadratic equation, right? It is a quadratic, so just use the quadratic equation here. Opposite of b is plus or minus the square root of b squared minus 4ac over 2a. And those are all the values input there, if we remember that quadratic formula cleanly. When we simplify the value under the radical, We have a negative radicand of negative 14,400. That's a problem, right? Well, it's not a problem, but it's something we're going to have to address. It's a negative number in a square root. It's a negative number in an even root. So it has an imaginary value. Note that the square root of 14,400 is 120, and that the square root of a negative 1 is I. So our evaluation of that radical is 120i. Now, when we simplify the numerator over this denominator of 2, we end up with 80 plus or minus 60i. So we get both, or we get two values for lambda. They're complex values, and we have 80 plus 60i and 80 minus 60i as our complex numbers, which are our eigenvalues. Okay, let's go seeking the eigenvectors for the eigenvector for 80 plus 60i. Notice each of these roots occurs once. So at most, each has one eigenvector or an eigenspace with dimension 1. So we expect to find one vector per eigenvalue at most. And in fact, we'll get exactly one because we can't have no eigenvector for each eigenvalue, right? Remember, we argued that through in section 5.3. If an eigenvalue does not have an eigenvector, then it wasn't an eigenvalue to begin with, right? Eigenvectors cannot be the zero vector. So anyway, A minus lambda I is this matrix here. We subtract 80 plus 60i as a group along the main diagonal of our matrix A. When we simplify that, we have this matrix. We can divide this matrix by 15 in both rows. That simplifies to this, just to make the constants a little smaller and more manageable. The crux step in this is to put this into row echelon and possibly reduced echelon form if we get a chance, but hopefully at least row echelon. And the way to do that is to consider that this is a complex number, this is a real number. I need to add a multiple of something to row 2, of row 1 to row 2 in order to get this 5 to cancel. There's nothing I can do until this complex number is actually a real number. Well, if we multiply a complex number by its conjugate, then the result is a real number. And so by its conjugate, I mean, I look at negative 2 minus 4i, and I change the sign in front of the imaginary number, the imaginary part of the complex number. So I multiply row 1 by negative 2 plus 4i. I'm not worried about row 2 right now. I just want to put a real number in the first entry of row 1. So when I multiply row 1 by negative 2 plus 4i, I'm multiplying both of those elements in the first row by that value. I get 4 plus 16 for the first entry. If you want to carry that out on your own, negative 2 minus 4i times negative 2 plus 4i, each of those pairs in parentheses, and be careful distributing things. And then I get 8 minus 16i in my right-hand entry of the first row. And now I'll have 20, 8 minus 16i. If I divide this row by 4, I'll have 5, 2 minus 4i. So maybe I'll add what happens in between here as an additional thing. Row 1 becomes 1/5 times row 1. So I just, or perhaps that's 4, sorry, 1/4 times row 1. Divide by 4, and I get 5 and 2 minus 4i in row 1. And that matches exactly the row on the bottom. So we've also added negative row 1 to row 2 after doing that. So a couple steps are combined here. But the key step was to get this, to use the complex conjugate to get a real number so that we could zero out the value below it. And simply doing that, we found that this row matched the bottom row, and we know that that will completely zero out the bottom row. So this is row echelon form. Pursuing reduced row echelon form is probably not necessary because the very next step, it's just a matter of dividing by 5, but we'll do that in solving for x1 anyway. It's clear that x2 is free. It has no pivot position in its column. So x1 will depend on x2 as follows, right? x2 being free, we write x1 down as this. Now here's a nice trick. x1 is a pretty complicated expression times x2. x2 is free. I can choose x2 to be whatever I like it to be. So if I choose x2 to be 5, as I've done here, the reason I've done that is because I know that x2 times 1/5 will cancel to 1, and that'll simplify my value for x1 a little bit. So here's that happening. We chose x2 to be 5. The multiple of 5 and 1/5 cancel, and we're just left with -2 plus 4i. That gives us a pretty clean looking eigenvector of x equals -2 plus 4i, 5. So there we are. We had a complex eigenvalue, and from it we get a complex eigenvector. We'll generally see at least one complex number show up in the eigenvector of a complex eigenvalue. So keep that in mind when you work on these problems. Now, if we repeat all of this in a very similar way, and we'll have a crux step here that's similar to this, where we multiply a row by a complex conjugate, either the first row or the second row, in order to get rid of a complex number in this first entry. It'll be the first row, now that I think about it. Then we can work all along the same lines, and we'll find that in this case, and we make a wise choice for x2 in this case, and we'll find that our eigenvector for 80 minus 60i, the other eigenvalue, is given by this vector here, -2 minus 4i, 5. So a comprehensive list of our eigenvalues in their eigenspaces is that for 80 plus 60i, it has eigenspace, which is the span of -2 plus 4i, 5. And for 80 minus 60i, this eigenvalue has eigenspace -2 minus 4i, 5. So there we've listed out eigenvalues and their eigenspaces. If we were trying to diagonalize this matrix, we could put these values along the diagonal in a diagonal matrix, and we could write each of these columns in their respective order to the eigenvalues as the matrix P, and we now have a diagonalized version of the matrix A that's given right here. Now, we're not asked to do so, and it's not necessary to, but maybe there is some interesting information to come out of that diagonalization, but we'll see something like it later on to sort of generalize it for 2x2 matrices. So now, just a quick review of some of the things we've used. The complex conjugate of a vector. We've already used the complex conjugate of a complex number, but that for a vector is, we'll denote it as x bar. And it's really the vector whose entries are the complex conjugates of the entries of x. And we're going to do an example of this down below. Another tool that we'll need is to know the real and the imaginary parts of a complex vector x. Remember, I talked about the real and complex parts of a complex number. Z equals a plus b I, right? We have z equals a plus b I. Well, for a complex number, the real part of z is a, and the imaginary part of z is b. No surprise there. You just b without the imaginary number next to it, right? Without I next to it. We just pull the real number out of each position. And that's what we mean by the imaginary and the real part of a complex number. For a vector, we just do this for all entries in the vector. Okay, we'll see an example of this down below. So they ask us to find the real and imaginary parts of this vector x. It's a 3 vector. And they want us to find the complex conjugate of x, which is x bar. So let's decompose the vector first. We realize that we can rewrite this vector x as, and this is maybe not a necessary step, but it's a good extra step just to understand all of what's going on here. We can rewrite this vector with the real parts in one vector. So that's a 0 plus I, a 0 plus 0, or 0 plus 0i, and a 3 minus 2i. So all the real numbers are 0, 0, 3, making up this real vector, or this portion of it. And then anything that has a multiple of I next to it, well, this is a 1, a 0, and a -2. So we have 1, 0, -2 times I. And we'll see that if we put this linear combination of vectors back together, we get our original vector. So the real part is 0, 0, 3. It's not times I, right? And the imaginary part is 1, 0, -2. It's the part that's times I. And again, note that maybe a little bit contrary to what you'd expect, the imaginary part of the complex number of the complex vector consists of all, is a real vector itself. And that's by design, right? We don't want the I to come with it. We just write the coefficients in some sense of I. And that's what we mean by imaginary part. So also the conjugate, which looks a little funny with x's arrow over top and the bar, but it means to take the conjugate of this complex vector. That means we move along, and everywhere there's an imaginary portion of our number, we switch the sign in front of it. So I becomes negative I, 0 is unchanged, and 3 minus 2i becomes 3 plus 2i. And that's exactly what we have below. And there's our conjugate for this vector. We'll use these tools at least once before we're done with these notes. So it's nice to have them well defined now. So some facts about these conjugates of complex vectors and complex numbers. Well, in our case, all of these will follow by using some of the basic properties of complex or conjugates of complex numbers. I'll demonstrate the first one. We have a scalar R, possibly complex, times a vector X, which is also potentially a complex vector. So starting on the left-hand side and getting to the right-hand side is how we prove one of these things. So on the left-hand side, we start here. Well, let's write down what that means. X is an n vector. We'll just assume generally it's got dimension n, so it keeps it nice and arbitrary. R times this vector looks like that, all underneath this bar, because we don't have this defined yet. We don't know what this means yet. We have to interpret it in light of the conjugate of a vector, not a scalar multiple times a vector, at least not yet. So this R times this vector leaves us with Rx1 down through Rxn, and we're going to take the conjugate of all of this. We're in a position to do so now. The conjugate of a vector we know how to do, right? When the scalar was in front, it wasn't defined. But now that we have this conjugate over a single vector, we're going to take the conjugate of each entry. And that's what the next part of this says. The conjugate of the vector is the conjugate of each entry. Well, we know from complex numbers that the conjugate of a product of two complex numbers, R and X1 and so forth, is equal to the conjugate of R times the conjugate of X1. Now that fact I've actually left as an exercise for students. If you're not familiar with that, or if that comes to you as an unexpected fact, or if you've just never seen it before, take Z1 and Z2 with this representation and show that Z1 times Z2 bar, the conjugate of the product, is equal to the product of the conjugates. And that's really simply a matter of writing down A1 plus B1i times A2 plus B2i and taking its conjugate for the left side, and then first taking the conjugate of this, which is A minus BI, and then this one, which is A2 minus B2i, and multiplying those two values together and confirming that the left matches the right. Then you'll have proved that this highlighted identity here is in fact true. And that's the identity that we use to go from this step to this step. Well, now we have R bar times each of our vector entries. So we can factor R bar out times the vector of complex conjugates, X1 through Xn. And the vector of complex conjugates, X1 through Xn, is just the complex conjugate of the vector by definition. And we've arrived at the right-hand side and we've proved our result. The print is not quite clear. There's a break between those two bars on the right-hand side here, as we see in some of the other cases more clearly. So this extends to matrices and constants, or matrices times vectors. It extends to scalars times matrices and so forth. So when we need these rules, we can just pull from them. So let's see, there was something curious about this main example that we've done here today, right? We had this eigenvector with its, or eigenvalue with its sister pair eigenvalue of 80 minus 60i, right? And we found this eigenvector looks suspiciously like this other eigenvector. In fact, when we look closely, we realize that this eigenvalue has complex conjugate, which is this one. And these eigenvectors are also complex conjugates of each other. If I take the complex conjugate of this eigenvector, the only thing I change is the plus sign in front of 4i, and I get -2 minus 4i, and I end up with my other eigenvector. Well, it turns out that's a general fact for matrices of real numbers, or n by n matrices with real entries and complex eigenvalues lambda. They're always going to come in pairs. So in other words, let's see this proven generally. If ax is equal to lambda x, and lambda x is a complex number with complex eigenvector x, then we take the conjugate of both sides of this. We'll use the facts from the previous page that the complex conjugate of ax is equal to the conjugate of complex conjugate of a times the complex conjugate of x. That's this line. And similarly for the right-hand side, we can split this bar over the two as products. And so we have a bar, x bar is equal to lambda bar, x bar. Now a bar, A is a real matrix and has all real entries. So its complex conjugate has no complex numbers, so nothing changes when we take its complex conjugate. So all of its columns are still the same. So A is equal to A bar. So we rewrite that in the next equivalence, or next equivalent equation. And we have A times X bar is equal to lambda bar X bar. And this tells us that X bar, the complex conjugate of our original vector, eigenvector X, as well as lambda and its complex conjugate lambda bar, form another eigenvalue eigenvector pair of lambda bar X bar. Right, and that's what this says below. Lambda bar is an eigenvalue with eigenvector X bar. We've just proven this generally. So if we ever know that a single eigenvalue lambda is complex and it's an eigenvalue for a matrix A, a real valued matrix A, a matrix with all real entries, then we'll know that its complex conjugate lambda bar is also an eigenvalue. And even better, we can find its eigenvector X bar really easily. Once we know X, the original X, we just take the complex conjugate and we get our second eigenvector for free, essentially, or for cheap. Right? And that makes computation really nice. And in fact, and this is our summary from the previous problem. In the previous problem, I did a lot of work after I found our two eigenvalues, which come out together as a pair. So it's not really that nice of a trick to know that you can just write lambda bar down as 80 minus 60i, but maybe it's reassuring to know that, or a good check to know that for this eigenvalue, we should also have its complex conjugate as an eigenvalue as well. So maybe it's best as a check. But once we found the eigenvector for this eigenvalue, and this was in fact how I did this when I set up the work for the notes, I didn't actually calculate the other eigenvalue's eigenvector, though one could do so by hand. I just used the fact that the complex conjugate of this vector is the eigenvector for this eigenvalue. So really basically what fact above this example is telling us. So once we compute one eigenvector that's complex, we just take the complex conjugate of that eigenvector and we get our other eigenvector that corresponds to the complex conjugate of the eigenvalue. So that's a really nice shortcut. We only have to find one for 2x2s of these. If we have a complex eigenvalue, we're guaranteed to have a second complex eigenvalue by all of this argument up here. And moreover, we'll know that we can get its eigenvector for relatively cheap once we know the first one. So our last example, or one of our last examples here, is to see the breakdown of if we have any matrix A, negative B, B, A. We really want to go back to this rotational matrix, right? We started with 0, -1, 1, 0 as a 90-degree rotation matrix. This is a more general rotational matrix. So we'll see what it actually does by decomposing it in an interesting way. So first we're asked to find the eigenvalues of A. So when we do so, setting this up, determinant of A minus lambda I, set it equal to 0. We end up with this equation right here. We have lambda minus A quantity squared plus B squared equals 0. It's our characteristic equation from this. Solve for lambda by subtracting B squared from both sides. Take the square root of both sides, plus or minus on the right, right? So now we've got plus or minus the square root of, this number is guaranteed to be negative, right? We've also assumed that not A and B are real and not both 0. So B is real and it's not necessarily 0. So we know that B squared has got to be a positive number. So negative B squared, as we have here, is guaranteed to be negative. So the square root of B squared is B plus or minus B. And the square root of -1 is I. So we get plus or minus BI on the right-hand side, and we just have lambda minus A here, and we see that lambda equals A plus or minus BI. So we have two eigenvalues, and they're A plus BI and A minus BI. They are complex conjugates of each other. Now we define, not to be confused with the determinant notation, we define the magnitude, or this will be called the modulus of this complex number. R is the modulus of lambda, which is the modulus of A plus or minus BI. And this is nothing more than the distance from the origin of the point A plus BI or A minus BI. We square the entries, the real and imaginary parts of A and B, add them together and take their square root. This is coming out of the Pythagorean theorem, right? So we look down at this little sketch down here. We've called R the hypotenuse of a triangle with side length A and B. So of course, R squared equals A squared plus B squared, when we think about A and B as coordinates in the complex plane. And so we have this relationship for R. So following up on this, if phi is the angle formed by the positive x-axis and the ray through 0, 0, and AB, well, that's this line here, starting at the origin, moving through AB. Here's the angle phi sketched for us as described, formed with the x-axis. Well, we can think about this in terms of polar coordinates, right? And it's really common and very useful to apply polar coordinates to complex numbers, A plus BI. So we can rewrite A, negative B, BA, our given matrix, our matrix that we know rotates things through space, in R2 rather. We can rewrite that as, well, A is R cosine phi, right? We know that from polar coordinates of this image right here. B is R sine of phi. So there's that. We have negative B, so we have negative R sine of phi, and so on for the bottom row. Well, we know, and what we'll do is we'll factor an R out of each one of these, right? So we have R out here. And what we have inside is a matrix that's of rotations, right? Cosine phi negative. This is our standard rotational matrix. Its magnitude, this does not rescale. This is a fixed scale rotational transformation, right? We've dealt with it several times. If we wanted to rotate by an angle of 90 degrees, we plug in 90 degrees here. If we want to rotate by 180 degrees, we do 180, or 30 degrees, we put 30 degrees in here, so on and so forth. So in none of those rotations with those values, where this matrix alone would change the scale of the vectors that we input into it. So it would preserve the scale. What will change the scale is the fact that we're multiplying by R, which is this sort of magnitude or distance from the pole or distance from the origin of the point A plus BI in the complex plane. So R times this matrix is the same thing as R times the identity matrix times this rotational matrix. So we can rewrite this as such. And what we realize is that for a matrix of this form, A minus BI, BA, having complex eigenvalue, A plus or minus BI for both of its eigenvalues, really decomposes into two things: a rescaling transformation, which is based on A and B, right? Depends on the values of A and B, and also a rotational component, which is really just based on the angle between the positive x-axis, or the real axis, we'll call it, and A and B. So that's a really interesting decomposition there. We rescale and we rotate. based on the angle formed by A and B in the plane, or the coordinate A, B in the plane, of the complex plane, thinking of this as values of A along the real axis and B along the imaginary axis. And yeah, so and this is all summarized down here at the bottom, but maybe some introductions to make is this. In complex variables, or when we talk about complex numbers, phi is called the argument of the complex number z equals a plus bi. It's denoted arg of z. And in complex variables class, you go more deeply into that, but it's such an important thing that this angle phi is actually defined. The angle between the x-axis and AB and the plane. And then the modulus, remember that distance from the origin, and the origin is often called the pole in polar coordinates or in the complex plane, is just simply that Euclidean formula for distance from the origin. So we have the argument and the modulus of the complex number z, and it turns out that the modulus and the argument of this rotational transformation matrix are make up a composition for, or a decomposition for, this rotational matrix. So again, this will also have some periodicity. Remember that this matrix here is periodic, right? In fact, how do we see that this is what's the simplest periodicity it might have? If we rotate something by 360 degrees, we'll plug in 360 degrees here. Well, that's 2 pi. Cosine 2 pi is 1. Cosine 2 pi is 1. Sine of 2 pi is 0. Sine of 2 pi is 0. This is going to be the identity matrix at 360 degrees. So the rotation has come full circle all the way around, right? And the only thing that happens to a vector that's under this transformation is it's rescaled by whatever r is based on A and B's magnitudes. So we'll see eventually, before we're done with these notes, that this is in essence what complex eigenvalues and eigenvectors mean in 2x2 matrices. And it generalizes a little bit loosely to n by n matrices, but not in such a clean and easy to see way. So here's that generalization by theorem. If A is a 2x2 real matrix and has a complex eigenvalue lambda equals A minus bi, with B being non-zero, in other words, it's strictly in the complex, or it's in the complex numbers and is not a real number, right? The B is not 0, so we don't just have a real number here. And it has an associated eigenvector V in C2, so a 2 vector with complex entries. Then A decomposes into P, C, P inverse, right? Where P we can build by just taking the real part of V and the imaginary part of V. And then C is equal to, it's not quite a diagonal matrix, but it is a rotational matrix. So this gives us a really interesting generalization. So even if A doesn't have this form, we know this is a rotational matrix. We know that it rotates and rescales vectors, right? We just saw that in the previous example. But for any matrix A that has a complex eigenvalue, right? And we've written it in the form A minus bi just because it's convenient for this formula down below. But if there was a plus here, we could change all that around as needed, nonetheless. So if we're given any matrix that has a complex eigenvalue, then we know that it is similar, based on this equation right here, it is similar to a rotational and rescaling matrix C. So this kind of sort of seals the deal. It tells us that 2x2 matrices with complex eigenvalues rotate things. They will in fact behave via rotation and rescaling, because they're similar to a rotational rescaling matrix C. And that's just a neat thing to keep in mind, because it means that any matrix that has complex eigenvalues has this sort of periodicity to it, as well as as well, or periodicity or rotation, right? Sort of the two different things. Periodicity might be violated if the rescaling is not 1, right? Because we can't get back to the same place if we're rescaling the length of vectors. They might grow too large or they might shrink too small and not ever have a fixed point for the matrix A. Nonetheless, let's go back to our primary example for these notes, this matrix A we've been dealing with. We know its eigenvalues, so we pick up its eigenvalue at 80 minus 60i, and we're going to just confirm that this theorem is true. Right? We're going to write down all these parts, and we won't prove the theorem. We're just going to see that this theorem is correct with this example, right? And again, that's not a proof, but it's a good introduction to using the theorem and to at least seeing one case in which it's true and perhaps extending that to believe it. So this eigenvalue has eigenvector given here. A is equal to 80 and B is 60. So we fill in C per the formula in the theorem to get A negative B, B, A, and it's 80, negative 60, 60, 80. And then P is equal to, well, it's the real part of V for the first column. So that's negative 2, 5. And then it's the imaginary part of V for the second column. And that's negative 4, 0 here. And this makes up P. And just following everything as in the orders that we're told to do, or that the formula dictates. And then, well, it's a good, now we want to check to see that this is actually true. We want to see that our equation up here actually holds when we build P and C according to this recipe, right? So, well, instead of inverting P, which won't be too bad because it is a 2 by 2, I just don't like the work of doing that. So if I want to avoid that and still get a reasonable check on this, I'll multiply both sides of this equation on the right by P to get AP equals PC. And that looks like this. Our original matrix A times the matrix P equals the matrix P times the matrix C. And you'll see that if you carry out the matrix multiplication on each side, that these two things will be equal to the same 2 by 2 matrix. So again, this is just an example of what the theorem states. I think it provides some intuition as to the theorem being true, but mainly we're concerned with the interpretation of it, right? As I've said before, any 2 by 2 matrix with any 2 by 2 real matrix with complex eigenvalues is similar to a matrix which uniformly rescales and rotates the vectors in its domain. So in other words, it rescales by the same amount each time we apply it, which is that factor of R. In this case, we could go about factoring. We could find R by doing the modulus of this. It would be 80 squared plus 60 squared, square root of that. And we could see how it rescales vectors based on that calculation. And it rotates the vectors in its domain. And we could find by what degree it rotates those vectors by, well, that would be probably an arctangent scenario, right? We know 80 is the 80 units on the x-axis, negative 60 units on the y-axis, and then you could write it. You could draw the situation and use arctangent. I think it'll be negative 60 over 80, and you'll take arctangent of that, which would be negative 3 over 4, and you'll get the angle by which things are rotated, our vectors are rotated. So that's nice to know. So again, any 2 by 2 real matrix with complex eigenvalues rotates and rescales the matrices in its product. And that rotation introduces this kind of an idea of periodicity, at least in the argument, right? We're going to rotate around and maybe around. And if the magnitude's increasing, we might spiral outward. If the magnitude's fixed, then we're just going to rotate, right? We might not rotate exactly in a circle. We could have an elliptical rotation as well. If A and B, I believe if A and B aren't equal to each other, then we'll rotate around an ellipse. If A and B are equal, I think that's when we'll get a circle. But that can all be checked more explicitly. Now, generally for n by n real matrices, it's a little bit harder to see, but what we can keep in mind is that if a general n by n real matrix has complex eigenvalues, it's always going to have a pair, right? Because we know that one complex eigenvalue has its complex conjugate also as an eigenvalue to the matrix, and they'll each have their eigenvectors, which are complex conjugates of each other. It introduces a periodicity or rotation into the transformations for the n by n matrices, right? So though it's a little bit harder to envision, maybe not so constructive to try to envision, but usually it's associated with periodic behavior, or sort of pseudo-periodic behavior. And that's where maybe we're not going to land on the same place, but our argument might be the same. We're going to rotate back into the same angle at some point later on in the applications of this transformation. So this becomes an important concept for dynamical systems, which are described by differential equations, and differential equations is potentially one of the courses you'll go to from here. So that's complex eigenvalues. Really, it's a matter of when you find a complex eigenvalue, find its eigenvector and use that shortcut to find it's the other complex eigenvalue as well as its eigenvector. And then just know that complex eigenvalues, matrices with complex eigenvalues, are associated with rotations or some sort of periodicity.